Hi, thank you very much, and good afternoon, good morning, depending on where everybody is. I'd like to thank the organizers for inviting me here today to give this presentation. It's really a big honor. So what I want to share with you today are some ideas that we, and of course many others, have been working on to see how we can incorporate concepts that we're used to from model-based processing, signal and image processing, into deep learning networks, where our goal is to develop deep learning techniques that are interpretable, that don't require a lot of data, and that generalize well to unseen data by using everything we know about the problem. So we'll talk about the concepts today, and we'll see some applications to imaging, although these ideas, of course, could be used to many other applications as well. So let me begin by, just saying that obviously today we're in the deep learning revolution period, and we know that deep networks achieve superior performance in many, many different areas, particularly in areas that are hard to treat using standard models. And examples are, computer vision, speech processing, where areas where coming up with very clean mathematical models is quite difficult. So we know that today, using deep learning, we could do, really remarkable things. So we could spawn fake faces, we could draw almost anything we could conceive of, we could get amazing classification rates, that far surpass human performance. But all of this comes with a price. So first of all, in order to get these good results, typically we need very, very large training sets, which are not always available. The training could be computationally very, very exhaustive. It's not really clear why we're getting a solution that we get. So very often there's this feeling that, if you kind of stir a little bit more, you're going to get a different answer. So the interpretability of the networks is not always very clear. And of course, a lot of the networks work very well on the data we train with, but it's not clear how well they generalize, how robust they are, and they're often very, very complicated. So GPT-3, for example, has 175 billion parameters. So that's obviously a huge number, and not something that's going to be practical if we're thinking of, putting a network in a car, in an autonomous vehicle, or putting a network in our cell phone as a communication receiver. So we really need, for some purposes that we're looking at, like communication, autonomous vehicles, clinical applications, we want methods that are interpretable, because an error could be, very costly. It could cost lives, literally, if we're looking at medical imaging. We want to be able to understand why we got our solutions. We want to be able to generalize well, and we want the complexity to be low so that we could easily retrain, and so that we can also do this on the edge, like, for example, on our cell phone. Now, if we look at standard signal and image processing, which are basically the techniques we used until, 5 or 10 years ago when deep learning became very popular, then these methods are very, very different than deep learning. So traditional signal processing is based on models. And the nice thing, of course, is that we can incorporate anything we know about the problem, any knowledge we have about the problem, any structure we have about the problem. It allows us to do inference from small amounts of data, so we don't need a lot of data to get a good result. And we also have very nice techniques that allow us to assess the quality of our output. So we also know how good we're doing, which is very important in many applications. Of course, the disadvantage is that this requires accurate model knowledge. We have to know the model very well in order to be able to get these good results. And the inference could be slow as well. So maybe we could get good results, but it may take a long time to get there. Now, what we would really like to do is combine these model-based methods with deep learning techniques so that we could get, simple interpretable methods that have the best of both worlds, that also incorporate what we know about the problem, but are also able to generalize and learn from the data itself. So to see how we could do that, how we could combine models with deep networks, I want to take kind of a bird's eye view on how model-based processing works, how deep networks work, and then we'll see how we could combine them. So in a traditional signal processing problem, you would start with some given input. We're going to call it here Y. And there's some desired output. So Y could be, for example, a blurry image, and the desired output X could be the clean image. And then you have some known relationships. So you assume that Y is equal to some function of X that you know. And then what you're going to do is you're going to search for the X that gives you G of X that is as close as possible to Y in some metrical sense. So for example, you might choose the X that will minimize the distance between the observation Y and this known function g of x. Now, typically this won't have a closed form solution. So what you're going to do is you're going to solve it using your favorite iterative algorithm, and then it will typically look like something like this. You have some pre-processing and some post-processing, and in between you'll have iterations that come from your algorithm, let's say from some gradient descent method. So this is kind of very abstractly what a signal processing algorithm would lead to, or an optimization framework would lead to. Now, if you look at deep learning, on the other hand, you'll have many paired inputs and outputs. In between, you'll have a fixed network that you decided on in advance. So, you know, this could be a CNN, a ResNet, whatever you chose to use. And the point is that the architecture of the network is fixed in advance, but you're going to use this training data, this paired training data, in order to learn the weights in this particular network. Now, when a new input comes in, you're going to put it through the network and hope that the output is approximating your true required output. So these are obviously two very, very different perspectives, right? The model-based approach and the deep learning-based approach. And what we're going to look at next are two methods to integrate them. So one is based on this really nice idea of unfolding or unrolling that dates back to beautiful work of Gregor and LeCun, where here essentially we use the optimization algorithm to give us the architecture of the network, to determine the layers in the network. And the second idea is a hybrid approach, where we integrate deep networks into model-based algorithms. Basically, we infer using the algorithm, but anytime there's something we don't know, we replace just that particular block with a deep network. So let me explain those ideas in a little bit more detail. So the first algorithm unrolling dates back to the really, really nice paper of Gregor and LeCun that looked at a particular instance, and over the years, many researchers have contributed to generalizing this. And we have a recent review that we wrote on algorithm unrolling, so you're welcome to go and take a look to see more details. And the idea in unrolling is that we start with our optimization algorithm. We then write down several steps of that algorithm. And up until this point, what we're doing is just applying, you know, t iterations, let's say 10 iterations of our underlying iterative algorithm. But then what we're going to do at the last step is that we're going to view each of these iterations as a layer in a network, and we're going to freeze some of the parameters so that we actually learn them from data. So we end up getting a deep network, which is actually typically pretty shallow, so we don't need a lot of layers because we're incorporating structure. And the layer structure is inspired by this optimization algorithm, but we learn the parameters from training data. So this is the first approach of algorithm unrolling. The second approach keeps the algorithm itself, so we end up inferring using the algorithm, but anywhere there's something we don't know, we substitute it with a underlying network. Okay, so these are the two main approaches. And if I try to kind of view them both abstractly, what we have is basically two sides, right? We have data-driven methods or deep learning networks on one end. On the other hand, we have model-based methods, which require domain knowledge. They requiring knowing the relationship between our inputs and what we want to infer. And, you know, there's many examples of model-based methods and of deep networks that we're going to visit some of them later on. And then in order to combine them, what we're going to do are two things. So in the first approach, we're going to infer using a deep network, but the architecture is inspired by our model, by the optimization approach. So this is the unfolding approach. And in the second, we're actually inferring using the algorithm, but we embed a network into the algorithm anytime there's something that we don't actually know in advance. So hopefully that makes clear kind of our philosophy on how we could do model-based networks. And what I'm going to do in the rest of the talk is kind of delve into examples and details. So we'll start with talking about imaging, and in particular, we'll look at general sparse recovery, kind of general imaging problems, and then focus a little bit more on ultrasound and super resolution. And then towards the end, we'll very briefly mention how we can use these ideas in other areas, like in communications. And finally, we'll end with a little bit of theory that we've been able to derive in the past few months, which establishes that really these model-based networks are better than networks that are not based in models in several different aspects. Okay, so let me start with the unfolding and kind of try to explain it in a little bit more detail. So in the unfolding concept, what we do is we start with an iterative algorithm. We then write out the iterations explicitly, as you see over here. So in a typical iterative algorithm, we apply the same block many times, maybe even hundreds or thousands of times. But what we're going to do in unfolding is we only do this a small number of times. And then each one of these functions has parameters that we're going to go ahead and learn from data. So let me show what this looks like in the context of a particular problem of sparse recovery, which was the original problem that Gregor and LeCun looked at. So we know that sparse recovery is a super popular method. It's used in many different approaches and in many different areas. The main idea is that we model our measurements as measurements that are given by some sparse vector, meaning a vector that has only a small number of non-zero values. We assume that it's observed through some linear transformation and corrupted by additive Gaussian noise. So for example, X could be an image that's sparse or sparse in a wavelet domain, and A could be the point spread function of the measuring system. So a part of the approach to recover X is to try and minimize the L2 difference between the measurements Y and the known model A, and of course the unknown X, where we add a regularizer on X to promote sparsity. And in particular, we could use, for example, the L1 regularizer. So if you go ahead and try to solve this problem, you could use, for example, a proximal gradient method. And this leads to the very well-known iterative shrinkage and threshold, the ISTA method, which was first proposed in this really, really beautiful paper of Davoshi's from 2004. And what the algorithm looks like is that it basically takes a gradient step. So what the gradient looks like is just these two blocks over here, and this is coming from this gradient step. And then we have a soft thresholding, which is basically the proximal operator that is coming from the regularizer. So if you were just doing ISTA, which is the proximal gradient solution to this problem, you'd be applying this block thousands of times until it converges to a sparse output X. What we're going to do instead in unfolding is we're going to take that basic block, we're going to write it down a finite number of times. And now, instead of assuming that these lambdas are fixed, the thresholds, we're going to learn them from data, and we're going to allow them to be different in each layer. And furthermore, instead of assuming that these blocks are fixed and depend on the step size and on the measurement matrix, we're going to assume that we don't know those parameters, and we're going to learn them from data. And this leads to the unfolding method that has the advantage that, of course, it's interpretable. We know exactly how we derived it. It generalizes well, and we're going to prove that later on at the end when we talk about theory. And it's able to infer using small amounts of data with a network that is pretty shallow, so we don't have a lot of parameters here to learn. Now, the very nice thing is that once we formulate networks as coming from optimization problems, we can use various different extensions of optimization in order to derive various different generalizations. So for example, a very important problem that many people look at in networks is how do we robustify networks? Meaning if our test data is different than our training data, how can we account for that? And what we suggest here is to say, okay, once we view this as an optimization problem, what we can do is we could use robust optimization, which of course was derived in order to robustify optimization problems, and then derive a new network that is coming from a robust optimization problem. And in that way, we'll naturally get a robust network. So in our particular case where we're looking at sparse recovery, what we could do is we could assume that we also have perturbation to the model matrix, and that's modeling our model mismatch. And then we can solve a robust problem where we're trying to not only minimize the noise and have a regularizer, but we're also trying to minimize the perturbation. Now, again, we could solve this using optimization tools. So we can show that mathematically, this is actually equivalent to this optimization problem, which is very similar to the optimization problem we had before, with the difference now that we have this extra normalization over here. And we can now go ahead and apply proximal gradient to this new objective. And this, of course, will lead to a different step, which when we then unfold will lead to a very different looking network. So this new network that we get looks very different than the previous network that we had. And what's nice is that we can actually show that when we have model mismatch, when the testing data is different than the training data, our approach gives much better performance than all competing methods. And the really nice thing here is that we didn't have to do anything heuristically. All we did is we used robust optimization, and it led to this network, but we didn't have to guess it. It was automatically given to us from the underlying optimization framework. Okay, so I hope I've convinced you that this is a very general framework and it could have many nice advantages. What I want to show next are some examples of how we can use this in imaging in general and in ultrasound in particular. So let me start with a very, very basic deep learning problem, and this is work done together with a group of Professor Vishal Monga, and he led this work. So here we were looking at a very basic problem where we have some sharp image X that we want to be able to denoise. We want to be able to recover this X from a blurry image, where the blurry image consists of an unknown blur and, of course, random noise. So in order to solve this problem, the first thing we did was set up an optimization problem. So we search for features of the image such that after we convolve them with this unknown blur, they will match features of the measurement that we actually got. And we add a regularizer on the features and a regularizer on the blur. Okay, so we just set this up as, you know, one of the simplest optimization problems you could think of. And then we do unfolding to this underlying optimization problem. And this gives us a network that has, you know, a very particular structure. This is not a structure you would have guessed in advance. It's a structure coming from this very particular optimization formulation. And the nice thing is that using only 10 layers of the structure, so, you know, a very small number, we could beat all competing state-of-the-art methods. And there's been many, many methods, of course, many advanced deep learning methods proposed for this deep learning problem. And we can see that using the simple unfolding, we do better than all of these techniques, even though we're using a very simple method. So you could see that both by looking at the images themselves, you see that we get much sharper images, we get much better resolution. And you can also see that by the various different quantitative measures where we outperform all existing techniques. Okay, so in what I showed now, we used kind of relatively simple regularizers. We used L1 and L2 regularizers, but we may have problems that are much more involved. Like, for example, maybe there's a whole entire area in the image that we didn't get in advance. Now, these are more difficult problems, and for those problems, we need stronger regularizers. So what we suggest to do, and this is work that was done together with Professor Ruud van Sloan and Daniel Friedman from Google. So what we propose to do is to say, let's also learn the regularizer. So basically, we're going to unfold the regularizer together with unfolding the algorithm. And we do that by assuming invertible flows on the regularizer, because it's just easy to do. And we parameterize the invertible flow, and then we learn those parameters together with learning the algorithm. And this actually leads to obviously much better performance. Of course, the network is a little bit heavier, but again, it's very principled, very interpretable. And what you see here are, you know, 3 examples of our approach. So these are 3 input images. These are their really heavily corrupted outputs, so either very heavy noise, very heavy blur, or areas that are just totally missing. And here you see our recovery using our method, and you see that it's much better than competing approaches that are more complicated and non-interpretable. Okay, so those were different applications for kind of blurring and denoising, but we can actually use these ideas for almost anything you can think of. So for example, you know, we can use this for signal separation. So a problem we get in ultrasound is that when we're taking ultrasound images, we see a combination of both blood flow and strong clutter from the tissue. And in this case, what we want to do is we want to separate the tissue from the blood flow. Okay, so this is a very difficult imaging problem, and you could get the same thing in many other examples. So you have the same thing in radar, for example, where you have clutter and you want to separate it from the desired targets. So what we do here is we model this signal as coming from low rank, which models the kind of static background, and sparse, which models the blood flow. And then we unfold this low rank plus sparse problem, this robust PCA problem, into a network. So before I go into details, let me just point out that we have a recent review, again, written together with Ruud van Sloan, on using deep learning for ultrasound imaging. And those of you interested in particular applications to ultrasound, you could go ahead and take a look at our review on this topic. Okay, so just to go a little bit more into the details, what we do here is we assume that our data is a linear combination of a low rank part and a sparse part. We add a low rank regularizer on the L on the low rank part and a sparsity regularizer on the sparse part. And then again, we use our proximal gradient scheme to recover the L and the S. So you just end up getting, you know, a gradient step and then soft thresholding for the sparse part and, you know, thresholding of the singular values for the low rank part. And then we go ahead and unfold this into the network. And again, you end up getting a network that is kind of very original. It's not a network that you would get if you were just using one of the existing networks in the literature. So, you know, it's a funny looking network that you wouldn't have guessed, but in our case, it's just following from the optimization algorithm. And we use, you know, 10 layers of the network, so very, very simple, and it does a really good job in separating the tissue background from the blood flow. As one more example in ultrasound, we've also used this to reduce the amount of data we need to form an ultrasound image. So ultrasound systems today are, you know, very big and cumbersome, and one of the reasons is that to form an image, inside the probe, we have many, many elements that need to be sampled and processed, and that's computationally very difficult. So we've used these model-based algorithms to help us choose, you know, which samples are actually necessary. And by the fact that we're able to reduce the number of samples we need, we can actually build very, very simple probes that replace the entire machine. So now that we only need a small number of samples, we can build a probe that takes only that small number of samples. It then transmits those samples over a Wi-Fi channel. So we no longer need, you know, this big machine and a cable. Those samples could be processed by any tablet or cell phone or in the lab to form an image. Or we can use that data to do even something more evolved. So because we could use the model-based ideas to represent the image using a small number of samples, we can now totally get rid of the machine and just have a small probe. And we also have access to the data itself and not just to the image.
Hello, everybody.
So I'm going to show a small demo from our group. This is Dr. Shaitai Manyoden, our cardiologist that we're working with.
Is an echocardiography of the subject's heart. We can
here he's scanning my former student.
Right now,
so the data is going from the probe directly to the local machine, to the remote machine, and to a tablet.
We can see the different structures of the heart. We can see the mitral valve and the tricuspid valve. We can see the nice motion of the leaflets. We can see that actually there is good ventricular function and there is no pericardial effusion. The picture itself is very good, very crisp, and we can demonstrate very nicely this subject's heart.
Again, here you see Dr. Shaitai scanning directly to the tablet. Now, like I said, not only could we get a small representation of the ultrasound signal, but now we actually have access to the data itself, and we can use that to get better images, for example. So this is, again, work done with Professor Ruud van Sloan and his group. So he's a really, really great collaborator, and we work with him a lot in the areas of ultrasound in particular. So here you've seen the data that we take, and we use a model-based approach to recover the image rather than standard beamforming, and you can see that we get much better contrast and much better resolution. We've also recently did a clinical study together with Dr. Ahuva Grubstein and her team in Beilinson Hospital. So this is Ahuva with her amazing team of doctors, Dr. Yael Rapson and Dr. Dror Suchami that we've been working with. And here, again, we took this raw data and used model-based networks in order to recover, and we could get much better resolution than we can using standard approaches. The other nice thing we can do is that once we have access to the actual channel data, we can use model-based networks to infer the quantitative physical parameters of this data. And what that allows us is not only to just plot an image like is done today in ultrasound, but to actually infer physical properties. So for example, we could plot here the speed of sound in the tissue. And you see when you plot the speed of sound that here there's a tissue that behaves very, very differently, and this is indicative of a tumor. But if you look at the standard ultrasound image, we don't actually see a tumor here. So by being able to process the data directly and using models, this is based on models of wave propagation, we can actually get features that we can't see in a conventional ultrasound. Another nice thing we could do is that once we could reduce the amount of data and do clever processing by relying on models, we could get very small devices, so wearable devices that could still preserve all of the important information. We've used these ideas in other areas, not just in ultrasound. So when COVID started, we started a task force in Israel with several different hospitals to see, where we could use AI to help them through the COVID pandemic. And one of the areas that at the time were very important in the hospitals was trying to get good detection very quickly. So by using these model-based ideas, we were able from a small cohort to get really good COVID detection from X-rays. And just to convince you that this is not an easy problem, you could take a look at these images. So these are images of 5 different patients, and some of them kind of you could determine maybe even by yourself whether it's positive or negative, but some of them are quite tricky. So for example, this image looks, the lungs here look very clear, but still this patient was positive to COVID-19. And then, this image over here, or this image over here is actually quite noisy, but still the patient is actually negative to COVID-19. So it's not so easy to do, just by looking at the images, and even trained radiologists could not always correctly detect the images, but using the model-based ideas in AI, we were able to get over 90% detection rates using very, very small cohorts of data. Together with a group of Professor Nobotelio Demi in Italy, we also applied similar ideas in the context of ultrasound. So trying to detect COVID from ultrasound, that's of course a much more difficult problem because we don't get reflection from the lungs, but we do get distortions that we could process using a model-based deep network in order to infer COVID. And this led to over 80% detection, which is quite impressive given the fact that you can't actually see the lungs in ultrasound. Okay, so in the time I have left, I want to switch gears and talk a little bit about how we can use these model-based ideas for super resolution, both in microscopy and in ultrasound. So one of the fundamental problems of microscopy is the resolution limit. So we know that we can't see details that are smaller than half the wavelength we use for illumination, which means that if we're using an optical measuring device, we can see, let's say, cells and bacteria, but it will be very difficult to see proteins and small molecules. Now, in 2014, the Nobel Prize in Chemistry went to this very clever idea of fluorescence microscopy, where the idea was to insert fluorophores into, the tissue that we want to image, and then to control the fluorescence of individual molecules, so that instead of taking one super resolved image, which is hard to do, we're going to take thousands of exposures, where in each exposure, only a small number of fluorophores are actually fluorescing. And then, if you have an image and there's only a small number of bright spots, you could go ahead and localize those bright spots, and in that way get a super resolved image. So this was a very clever idea, led to the Nobel Prize, and it gives very good spatial resolution, so on the order of 20 nanometers. But the problem is that you need thousands of measurements now in order to get one super resolved image, which means that you can't use this for live cell imaging because it just takes too much time. So you can't have the cell change between those different exposures. So what we want to do here is to see if we can use these ideas of model-based processing to get very good spatial resolution, but also very good time resolution, so that we could do this quickly and pave the way to live cell imaging. So to do that, we exploited the fact that these fluorophores blink in an independent fashion. And therefore, if we look in the correlation domain, we know that the correlation matrix between the images is going to be sparse because they're uncorrelated. And the variance itself, the diagonal itself, is also going to be sparse because not all the fluorophores are blinking at the same time. So by exploiting these two underlying principles of fluorophores, we developed a method together with a group of Professor Moti Segev at the Technion called SUPARCOM, Super Resolution Correlation Microscopy, where basically we relied on the structure in the correlation domain and the sparsity in particular in order to get better resolution. So this is still not using AI, this is just using a model-based algorithm. And here you see our method SUPARCOM, and you see that we even get better resolution than the method behind the Nobel Prize, but we're using 2 orders of magnitude less images. So we're using around 300 images and they're using 12,000. Okay, so this is fantastic and it paves the way to live cell imaging. The difficulty though is that to get these good results, we had to play around, with the optical setup and with hyperparameter tuning. So it's not totally, straightforward. So instead, the next step was unfold this method. And after unfolding, which led to what we call Learn SUPARCOM, we get remarkable performance, so even better than what we get before. But the most important thing here is that we didn't have to do anything. We didn't touch the system at all. So all of this is learned from a single image. And therefore, it's totally generic and can work with any microscope. So we were very excited about these results, and we started to work with a group of Professor Gilad Daran at the Weizmann Institute to see if now we could do live cell imaging at high resolution, which couldn't be done before. So before, to get high resolution, you couldn't look at dynamics. And for the first time, we started looking together with Gilad, who's of course doing all of the measurements, we started looking at dynamics of T cell activation, and we're able to see it at this high resolution. Now, the next thing we wanted to do, especially when we have long videos, is to say, okay, we even go one step beyond where we don't have to learn anything in advance, and we learn everything from the single input that we get, or from the single video that we get. So this is what we call auto SUPARCOM. We learn everything only from the actual input data. And again, we do this by combining the model-based approach and the unfolding approach, and you see that it can work really, really well. So these are the original frames, and these are the super resolved frames in real time. Okay, so those were the results we got in microscopy, and then we wanted to see if we could take them over to the clinical domain. And to do that, we chose to look at ultrasound imaging. So of course, to do ultrasound imaging, you don't want to inject fluorophores into the body, and you probably can't inject fluorophores into the body. So the question is, you know, how can we get the super resolution? And we did that by using these microbubbles. And this is FDA approved, so these are contrast agents you could use for ultrasound. You inject them into the bloodstream, and once they're injected into the bloodstream, they flow through the blood, and this makes them very similar to the fluorophores in the optical setup. So we can now track these microbubbles, and if we could localize them, we could basically get super resolution, just like in the microscopy problem. So we did a clinical study with a group of Dr. Huva Grubstein that I mentioned before, and we looked at 20 female patients with different breast lesions, both benign and malignant. And the important thing to note, though, is that by just adding the contrast agents, we're not actually getting better resolution. So here you see a lesion without contrast agents, and here you see the lesion after contrast. You see that it just makes everything brighter. It doesn't actually give us more insight into the lesion. But after using techniques, model-based approach I used before, we can actually get very good depiction of these lesions. And these images are obtained from these images just using our post-processing. And the other important thing to point out is that we didn't do any training here. Everything is learned from the given data set. So what you can see is that these three lesions that here look very similar to each other are actually quite different. So here we see, you know, a very oval that is very homogeneous, and this is indicative of a benign lesion. Here we see that the inside is all fluids, and this means that it's actually a cyst. Here, unfortunately, we have a malignant tumor. So we can see that, you know, we have a very high concentration of blood vessels at the periphery and very low concentration in the center. And also the shape here is very irregular. So we could see that it's a malignant tumor. But if you look over here, it all looks the same. So this kind of shows the power of these model-based networks for super resolution. Now, here again, we could do all of this from a single image using very similar ideas to what I presented before. So basically, just to delve one step further, we use an encoder-decoder model, but we do a model-based version of it. So we use models in both the encoder and the decoder, just like I explained before. And this allows us to get, you know, super resolved data. This is the original data, and this is the super resolved data by only using the input itself. We don't use any prior information other than the input itself. Okay, so that was kind of the main thrust of what I wanted to share with you today. And let me just take a few minutes to wrap up by discussing a little bit about how we can apply this to a different area, communications, and then I'll point out some of our theoretical results. So again, I'm not going to delve into details here, but it's just important for me to point out that these ideas are not necessarily tied to images. So the same model-based ideas could be used in many other areas. We've been using them for clinical data like ECG, EEG, which are not images, and we've been looking a lot at communication networks. So one of the first methods that we derived together with a group of Andrea Goldsmith and Neil Schlesinger is the Viterbi net, which is basically a learned version of the well-known Viterbi decoder, which is used for symbol detection in, you know, all of our cell phones today. And what we showed is that instead of replacing the Viterbi decoder by an end-to-end network, we can use this model-based approach to keep the beautiful structure of the Viterbi algorithm, which is based on dynamic programming, and just learn one block, the likelihood block, but keeping everything else the same. And this allows us to approach the same performance of Viterbi as if we know the channel statistics, even though we don't, without having to use any overhead. So everything is learned from the given pilot sequence. We could do the same thing for many other algorithms. So we can use this for factor graph methods where we have an underlying probability distribution that we decompose into factors. And we know that if we have factors, we can use message passing, which is a very powerful algorithm over the network. But what we do instead of replacing all of this by an end-to-end network when we don't know the distribution, is we keep the message passing and all we learn are the factors. So again, this allows us to incorporate the model together with learning. We've used this also for successive interference cancellation or for greedy methods. So it's not only for optimization-based approaches. So let me now end with just 2 slides on some of the theory. So I've said many times that these model-based networks are better than, their version without models, but we've seen that in all of the applications we've shown, but the question is whether we can quantify that from a theoretical point of view. So very recently, together with Professor Miguel Rodriguez and my students, we were able to show, 2 really nice results in that direction. So the first result we can show is that we could bound the generalization error of these model-based frameworks, and we've looked specifically at unfolding methods for sparse recovery. And what we can show for the first time is that the bound on the generalization error actually decays as a function of the number of layers. Now that's of course very intuitive, but in the literature, if you look at all the results today for generalization error do not decay as a function of the layer number. So this is really the first result that shows that the generalization error can decay and is of course better than the generalization error we get with a non-model based network. The second aspect we looked at was the sampling set, the training set that we need in order to, for example, get 0 training loss on the training data. And what we were able to do is to get a bound on the number of samples that we need. And of course, we can show that it's smaller than the bound that we need on a non-model-based version. And furthermore, it allows us to compare directly between different model-based networks. So to end, we've tried to develop a framework that merges signal processing algorithms with machine learning tools. We've shown that this could lead to much better performance from very small training sets. It allows to incorporate various forms of domain knowledge. It gives us, interpretable methods. And although the theoretical analysis is still in progress, we have some beginning of results that show that not only does it work in practice, but we can also show theoretically that this works better than non-model-based versions. So those of you interested, we have several reviews on our webpage where you can see many more details. I'd like to thank my amazing group of students who've, of course, contributed to all of the work that you've seen here today, and my amazing collaborators that I have the pleasure and honor to interact with. And thank you very much for your attention. If anyone is interested in these topics, I'll be very happy for you to reach out. We're always happy for further collaborations. And with that, I'll end, and I'm very happy to take questions.